topic today is demand response. What is demand response? Well, we will see in a few examples, and we'll do a little bit of theory of demand response. A little bit, because the major part of the theory of demand response is MPC, Model Predictive Control. This is how demand response is really implemented, and we saw that last week. A bit of terminology. Demand response is one of the most visible parts of smart grid. It's not necessarily the most complex and most important one, but that's one that is visible to consumers because demand response has to do with manipulating the demand, the consumption. There are subtle variants in terminology. Some people make a difference between demand response, which is manipulating the consumption by prices. The idea being that if the price of electricity is higher at a given point in time, then users will adapt to it. Like we saw last week when we saw David's house, how we would heat it. We would take into account with an MPC the prices of electricity, and the MPC control will try to avoid using electricity when the prices are high. So that's one way to incentivize consumers to not consume when the prices are high. Sometimes there is another variant of that receives another name. It's called demand side management, which has to do with the direct manipulation of electricity consumption. In economical theory, we can do control of demand either by prices or by direct control. Directly controlling means preventing you from using more. This is what is done by having, for example, your electric utility manipulate your user appliance. As we will see, those are more old style, but those are systems that are developed now in countries where there's a lot of heat of air conditioning, for example, where the utility might decide to switch off your air conditioner at a peak point in time. In this lecture, I will not do the subtle difference between demand response and demand side management. So if some people complain about you writing this or that, be aware that some people might be picky about the terminology, but I think the terminology is not exactly stabilized here. Before diving into the topic, let me ask you this question. What do you think is the real goal of demand response? And you think majoritarily that your answer is C, to optimize management of the electrical grid, and that's the stated goal. Yes, that's the goal of demand response, is to make the management of the grid, and in particular of what in the grid, of the matching between generation and consumption, which is the hard problem of any electrical grid. So matching consumption and production is facilitating the matching is one of the goals of, is the primary goal of demand manipulation or demand response here. As we will see, sometimes some demand management operators claim that their goal is to save energy, but as we will see, that may or may not be the case here. Reducing the cost is perhaps the long-term effect, but it's not certain that is the primary goal or even what we will achieve. What we will do now is look at a number of demand response projects or deployments that have been done, and that will help us see the variety of things that can be done. Here is one of the motivations for a demand response. That's the power consumption here in France on a cold and average November week. Right? So this is a cold week, and this is an average November week here. So that's the production here. The production is characterized by the fact that in winter, the electricity grid is under stress. This is where there is less of solar energy and more of demand, at least in cold countries like most of France, most of Switzerland, where the peak consumption is for heating and is in winter here. And what we see is that also the consumption is very irregular over a day. There is a peak at one point in time, which is typically the beginning of the evening, when people go home and they set up all the appliances and their house is perhaps a bit cold, they put it warmer as well. And now if you are responsible for the transmission network of France, you have to make sure that the total capacity is equal to the peak here. So, what's the problem with that? We need to over-design everything. So it's an economical problem. It's possible to create resources that will produce that amount of electricity. But the economical problem is that the investment you need to produce this will be recovered at very, very rare periods of time. So no economical agent will be willing spontaneously to produce the capacity to allow for the peaks to occur. That's one of the problems. One of the economical problems in grids today is that finding incentives for investments to produce the capacity that will be needed very, very rarely. So anything you operate and has a very low duty cycle is an economical problem. The solution is to make this extremely expensive. So if you can sell electricity during this peak for 1,000 times more than the regular price, then you will find investors that are willing to invest in such equipment. But then it's not obvious whether there will be social acceptance of this. An alternative to that is if you can reduce these peaks, which is called peak shaving. Right? So this is, if we can avoid this by, for example, having heating systems that have some inertia, and providing signals to consumers, perhaps via prices, perhaps via other mechanisms, to incentivize people to not use at the peak time here. So peak shaving has been one of the very, very old topics in grid management and has been one of the systems that have been, one of the incentives and one of the systems that have been early deployed here. Now, today we have even more exacerbation of this. So we have a lot of loads that are called elastic. Of course, what can you manipulate? It's only the things that have some elasticity. Here, the beamer, for example, is not an elastic load. I cannot decide not to use it now because we're teaching here, so we need it here. So lots of the low consumption devices that are in homes are not flexible. The lighting, all the equipment we use, the TV when there's a football match or the news in the evening, this is not, so all those things are not elastic. But all the thermal loads in particular, if there is some inertia in the thermal system, then can be manipulated, as we've seen in the MPC last week. Right? Your house with some time constant can be delayed or anticipated here. Some people claim that washing machines are also elastic, although some others would not agree. But that's certainly one system to which demand response can be applied. And here I'm showing the problem that your generation in the grid, for those of you who will be confronted with grids, will have to solve. That's the problem of electric mobility. Electric mobility will cause a huge increase on the consumption of the grid. The estimations vary, but if we would transform all of Switzerland mobility to electric, ABB's estimate was that that would double the grid consumption. Of course, that's transforming everything. I mean, all the trucks that go to Migros, all that thing, assume they would become electric. Half of the mobility is for companies. They use diesel today. So moving all this to electricity will be a large impact on the grid. On the other side, there's more stress on the grids because generation is becoming more of a problem for various reasons. Some people, some countries refuse to have nuclear energy. Energy that you produce a lot of CO2 we try also to reduce it. So there is a stress on the grid, more consumption, so good business for smart grid people. Here is an example. So many countries have tried to do effective demand response. Here's an example that has been published in the literature that shows you very typically what can be done. You may remember when we studied the OPF problem, the concept of locational marginal prices. The price of electricity can vary dramatically if we use locational marginal prices when the grid is not over-dimensioned, when the grid capacity is not able to support everything, which happens in many places in Europe and even worse in other countries. So one of the things that have been tried here, this is in Norway, is to, so here is the prices on the real-time market that are reflected to consumers at home. So I mentioned that we could use a price signal to consumers. Here is what they tried in this pilot experiment. So that's the price of energy. It's around 5 cents per kilowatt hour. That's, I would say, the standard price of energy in Europe. That's not the price of electricity, because when we buy electricity, we pay much more than this. Why? Yes? Transmission grid, and also what is called the distribution grid, which perhaps you had included in transmission. So the grid itself, I mean, practically half of the price of electricity is running a distribution grid, which is paid by volume, even though in fact much of the costs are independent of volume. It's not the energy, the production of energy, it's just making the real-time balance every second. That costs a lot here. So here that's the price of energy that's made visible to consumers, and we see that it can go from 0.05 to 0.25, so it can be multiplied by a factor of 5 here. Users received the information at which period of the day this could occur. Here it's at the morning peak and the evening peak. So consumers knew that at this time of the day, here is the price that they would have if they buy this kind of service. In contrast, the price would be very low for the rest of the day here. So users became aware of those things here. And here it's, I would say, a social engineering type of demand response by trying to have people simply not wash, for example, with the washing machine or the dryer at some of those periods of time here, which may be a trick if you have to do it in the morning. So hopefully you have a timer on your machines here, right? So they applied it to mundane appliances. And the study that is given in reference in the lecture notes found that it worked. So here you have the impact here. In green is from a standard averages here, and in blue is the curve that you see in the measurements that have been done with this experiment. So we see that people do consume less when the prices get high. Right? If you observe this curve, yes. Exactly. So that's one of the issues of demand response, is exactly this, right? It's fairly easy to reduce consumption during a short period of time, but what you expect when you do this is what is shown here. Anticipation, that may occur here. This is in countries where people anticipate, Norway, obviously. And rebound. The rebound effect is the fact that after that you heat more. If you use it for heating, then of course your house is a bit colder at 10:30, and then all heaters start up again. So there is this effect that has to be somehow factored in if you do a demand response program. Right? That's the very important part of it. There's a dynamical component in demand response, which is typically not incorporated in the theoretical economy of demand response, but that any grid operator is well aware of and will need to factor out. Nonetheless, they found that this had a price, this had an effect on the price. The price between inside Norway, so Norway is an example of grid which has a lot of generation in the mountains with hydro, which is far away from the large urban centers, and then the location prices may depend very much on the demand. If you reduce the demand at the peak period, then you will reduce the price here, which is shown here, showing the prices between two regions, and you see that there is a large difference of prices, primarily during the peak of the peak period of the evening. We'll come back to such graphs here. We will see how economists interpret the impact of load reduction on prices here. Here, that was one of the objectives here. There are more classical examples. For example, in this region, if you buy a subscription from Romande Energie, which is one of the major companies in the region here, you can have a normal service, or you can have a time of use tariff, which gives you different price at night and during the day, for example. This is very typical of nuclear countries. When you have generation which is nuclear, the generation is constant when there is no security stop in the nuclear plant, which occurs still with probably about 15-20% of the time. But most of the time, nuclear energy produces a constant amount. And as you know, a nuclear power plant is from the electrical viewpoint, is an extremely primitive thing. You just boil hot water to make a turbine that produces electricity. So once the hot water is produced with the nuclear reaction, there is no control on it. You just have, the only control you can do is to let vapor go out in the atmosphere to reduce the production of electricity, but this is wasted. The only thing you can do is curtailing, and this is wasted. So nuclear energy produces a constant amount, and what many countries have done that have nuclear energy, like Switzerland or France, is to make systems to incentivize the consumption to be as flat as possible, to be the same over 24 hours. What is done is, for example, to have all the boilers that we have typically in Switzerland and France. You don't have hot water that's produced on demand, but that's boiled during the night when fewer people are consuming. So you let the boilers work at night, and to incentivize people to do that, you give them a tariff that is becoming lower. So that, I would say, is old-style energy. Now, when you start having a lot of renewable supply that is non-controllable, like solar energy, typically, the peak production is not, and the problem is not necessarily exactly to shift consumption from day to night. For example, when there's a lot of solar, the peak generation is around noon. So in Norway, we saw that in their generation system, there is a high price at noon. In countries like now in Switzerland, that's the opposite now. In May, June, there is a large production of solar energy around midnight, so the prices of electricity drops around midnight. So you want more flexibility if you're an operator. You want to incentivize people to boil their water when the price is high, is low, which might be over lunch, for example. So there is, for example, a service that is called interruptible supply, which is a primitive form of demand response where the operator can exercise a relay on one of the phases that will stop the power consumption on this phase under the control of the operator. So the operator can say, I stop your boiler, for example, or I let it go. That is called interruptible supply, and this is typically done for heating space or space heating in the Alps or hot water here. Those are examples where you manipulate directly the load here. Here is a third example, which is larger scale and more modern. It's called Voltalis in France, and it's based on, so the old system of interruptible supply are based on signals that are sent via the electrical cable. They are called ripples. They are little very primitive signals. So you don't send internet packets over those lines. You simply send a signal, which are in very low frequency signals, and there is a device on the relay that receives this signal, and there are two signals, on and off. Right? So when you receive the off signal, the relay goes off. When it receives the on signal, it goes on here. More modern things is to use cellular telephony. So this company, Voltalis, produces a device that is called a Blue Pod that is connected to your electrical panel, also has a GSM antenna, And then the Voltalis company sends messages to the blue pods that interrupt a relay that switches on or off your boiler or your electric heaters here. So this is, again, an interruptible load, except now it's very dynamic. Short time also. The interruption, they claim, is never more than 1 hour per day. And the peculiarity of this one is that Voltalis does not make any money contract with the consumers. The final consumer does not receive any money for that. Other programs in North America, Canada, Ontario, the US, do similar things, but with incentive payments. So here the incentive payment is that when we interrupt your load, you receive some money, directly or indirectly, in the form of a credit on your electricity bill, for example, here. In the US, this is typically to control air conditioning. In France, it's to control boiler and resistive heaters. So what does Voltalis, where does Voltalis get money from by doing that? Imagine you're Voltalis, so you're sitting in a control center where you're controlling 1 million houses that have boilers and things like this. And the thing you can do is press a button to send a signal to those houses to say, stop now during 1 hour. What's the effect of this? Yes?
The company who had to produce for the peak will pay a little bit less for the company?
The company that has to produce for the peak will pay less, exactly. Indirectly, this is what happens. So Voltalis plays in what is called the real-time market. So the energy market, as you know, is done in, depending on the countries, is done in several stages, typically day ahead, and real-time. Real-time means 1 hour or 2 hours before execution. So when the operator, the European transmission network operators observe things and see, oh, this is a very cold winter day, we have a small problem, can someone produce 1 gigawatt more? So they will make a bid, make a call for that. And then companies have to agree on starting, for example, if you own a gas generator that is very expensive to run, very expensive to start, for example, and then you burn gas when you run it. You may decide or not decide to fire it on, depending on the price. Right? So you advertise your price typically, and if the price is good for you, you will run here. This is how the real-time market works. And here we're talking of hundreds of megawatts or gigawatts here per operator. Voltalis does exactly that, except they cheat in some sense. If the French transmission system operator says, I need 1 more gigawatt, then Voltalis can raise their hand and say, I can produce for you 1 gigawatt, which is in fact 1 gigawatt of reduction. So that will be visible on the market, that the reduction will occur. So it's like a generation here. This is the business model on which they live. Of course, this causes a number of problems. In particular, well, there is a rebound effect, so probably this will cost somewhere. So this has to be anticipated by the TSO. And also, when they reduce the consumption, perhaps some of this, they may reduce something that has already been sold by someone else. For example, a generator company might have sold to consumers some electricity based on their forecast and the dispatch plan that was done the day before. Now this may be reduced, and the reduction means a loss of revenue for the generator companies. So there are tricky issues on where does the money go. So typically in France, for example, the court said that Voltalis has to share its revenue with the generator companies. Nonetheless, it's a useful system to avoid, for example, starting a polluting peak power device here. Here is a third example. So before going to this third example, so this is an example, this is a picture that is taken from Swiss Federal of Energy, and so I think is the original source, that is explaining the 3 time scales of control of the European continental grid. And the same principles are applied to practically any grid. So all this pink set of countries is the continental European grid, which means that all the systems that are in this area here react together for the power balance. They are synchronized together. As you see, part of Europe is missing. The UK is separate, so Great Britain is one island, which is an autonomous system from the balancing viewpoint. It is connected, of course, to the mainland. It receives energy and can send energy, but mainly import, but the balance is done locally. It's not what we call synchronized in frequency. We'll see why we talk of frequency in a second. There are other parts like Scandinavia, the island parts of Denmark, I think, and Scandinavia is also separated. Ireland is yet another system. Why did I speak of frequency? Well, frequency is the frequency of the electric AC wave, so 50 hertz, the main frequency, is the first signal of power imbalance. Why is that? The frequency is nominally 50 hertz. Here is an example of the frequency measured somewhere in Europe. The frequency is not exactly the same everywhere, but practically the same everywhere in an internet connection here. The frequency is nominally 50 hertz, but it varies a lot. By minuscule amounts, here we're talking of 50.06 or 50.935 here. But it varies, it does vary all the time here. When the frequency is lower than 50 hertz, what does it mean? Yes, load is larger than generation, so there is a generation deficit. And why is that visible in the frequency?
It's too slow
There is?
The generators are too slow to provide power.
The generators are too slow, exactly. So this is based on the idea that the generators are big rotating machines. There are turbines produced by heat or by diesel. So if you have a diesel engine and, for example, a car, right? If you're driving a car and then for some reason you're getting into a slope, so it's harder for the engine, what does the engine do as first reaction? It slows down, right? So by slowing down, it delivers some of its mechanical inertia, which will dampen the overconsumption, but it will slow down. So slowing down, if the frequency is given by generators, means that the frequency also will go down. So if you have a small house in the Alps with your own diesel generator, and that's your grid, a diesel generator and the rest of your house, then the frequency will vary by huge amounts, not by small amounts like here, but it will vary dramatically. It will go down to 40 hertz, and you hear it. You hear the generator having problems, or it will also become very fast if for some reason the opposite occurs. So you disconnect a load. So that's the very first thing. That is at the root of everything. So originally, because AC grids have been made by big rotating masses that are the generators, when there is a power imbalance, it's immediately visible on the frequency. So the inertia of the generators mitigates the imbalance, so it has a stabilizing effect, but only for a very short amount of time. But that's the first stabilizing effect that AC grids have been living on over decades. This is why AC grid is such a powerful system. But of course, if you pull too much on your diesel generators, then if you don't do anything, there will be a problem. So what do you do in your car when you're driving and the slope becomes steeper? You do something, you give more gas, or you change gears, or you do something to produce more torque to re-establish the system to a good state. This is called primary frequency control in electrical grid. Traditionally, primary frequency control means all generators have what is called a governor, an automatic gas pedal that senses the frequency the speed, which is the derivative of the phase of the rotors. And when the frequency is going down, it gives more gas. When the frequency is going up, it gives less gas. This is the traditional way of running a grid. This is how grids have been running over a century. This is called primary frequency here. And that's the main mechanism that gives the power balance in real time. So whenever we switch off boilers, for example, if there's a football match in the UK and during the break everybody switches a boiler on, the boiler is 2 kilowatt times 2 millions, that makes 4 gigawatts, right? So football match break plus 4 gigawatt. Then you don't have time to call the market to do things. So this is done automatically in real time and is called primary frequency control by having all generators having some spare capacity, not all, but the generators that provide a primary frequency support. There is a market for this frequency support, and they sense the frequency and then they react to this imbalance here. That's the first thing. There are 3 timescales, and here this is illustrating a more catastrophical effect, which is here a power plant outage in France. So in France, one nuclear plant is taken out of service because there is an alarm. Nuclear systems are extremely scrutinized for security. Whenever anything is suspicious, there is a risk that you stop the entire plant. So this is happening here. You lose, let's say, 1 gigawatt here. Immediately, you will see that there is a drop in frequency. And during this short amount of time here, during here half a minute, primary frequency kicks in and stabilizes the system here. However, it was not able to come back to 50 hertz, which means that here, that's an example where the primary frequency reserves are not sufficient. There is a second type of reserve, which is called secondary, which operates on a larger time scale using explicit systems. So you have generators that are working only for this or providing a secondary reserve service and receive a signal, for example, from Swissgrid or other TSOs, and that they have to follow this signal. So this signal tells them how much they have to produce, more or less. So it's an explicit signal. It's not like primary frequency, which is embedded in the generators and have them modulate their actual production. The secondary signal is an explicit one, and then it goes to all the generators that have made available their capacity for that type of thing. Here we see that the secondary reserve kicks in, but is also not able. So the secondary reserve is across the entire interconnection. The primary frequency response which occurs here is across the entire interconnection. So when one nuclear plant has a failure in France, all generators in Poland react by generating more, and all over Europe here. And because we have a huge system, the inertia of such a system is large, and that makes it stable. Does not exclude catastrophic failures either, but it makes it very stable here. Then the secondary response that comes in later is typically under the domain of one transmission system operator, for example, France in this case here. So it's the responsibility of this local system, local from the viewpoint of Europe, to bring back enough capacity, which is done typically in this time here, by calling generators that participate in the local market. And in this case, this did not work, so then there is a larger time scale here, which is over 1 or 2 hours, which is called tertiary frequency control, where here you send fax or you send a mail or you call someone to say, now start something, a power plant that was down. So those power plants for secondary frequency control and primary frequency control, they are ready, they are working, they just are able to modulate their power. They have to react within seconds for secondary frequency control, instantly for primary frequency control, and here they react in a time scale which is order of the hour here. And hopefully there is enough capacity to start, here you have 3 power plants, one in Spain, two in France, that are compensating for the loss of this. So we see that it took around 10 minutes to activate the final response to this failure here. So this is how the grid works here, in this room, everywhere in Europe. This is why we extremely rarely have blackouts. Most blackouts we have, like the one we had a few weeks ago, are due to distribution network. A short circuit somewhere on the line, an insulator that has a problem, a transformer that has a loss of something somewhere. So those are local blackouts that may kill part of a grid, but complete blackouts that bring down an entire country are extremely rare. The last major one was Italy in 2003, so 16 years ago, where the whole of Italy was disconnected from the grid, but that's extremely rare. And the reason it's rare is because of this system here. That's the state of grids. That's the one that has evolved over decades, and that's very sophisticated now. Renewable energy make this worse, because renewable energy introduce more randomness in the system. What is the randomness in a classical system like this? The load. The load is random, but at the time scale of huge interconnections, in fact, it is extremely little random. French EDF, they claim that they can forecast with an accuracy of 1% the consumption of a region in France, right? Day ahead. Right? So because we human beings are very, very predictable, of course, you need, over the time, operators have evolved extremely sophisticated forecasting systems where you forecast using time series analysis, machine learning, and all that stuff, but also social engineering. You know, if there's an event of some kind that happens, then the behavior of people might be different. You need to take into account the fact that people are on vacation or not, etc. But over the years, this has become very sophisticated and works very well. So there is some randomness in the load, but not so much. The other source of randomness is the failures. Failures in the grid. That was the case that caused the Italian blackout. It was a failure in transmission lines in Switzerland. In fact, the lines had been touching trees. So failures in lines, transformers, major infrastructure that are in the transmission network, or of course generators. So those are I would say the classical panorama is this one. You forecast the load. You know there is a risk of anything going wrong. So what you do is you have a bit of reserve. So of course you put more generation in place than what is strictly needed, so that if at least one of the major generator goes away, you'll be able to recover. Plus you put all this system of reserves here. Now what happens when you have in June a lot of sun and wind? Then it may be that in Northern Europe, for example, up to 50% of energy is renewable. And we hope in 50 years, perhaps 100% of the energy is renewable. Then we need more of this. We need more of the reserves. We need the fluctuation will be much larger. So a side effect of renewable energy or randomization of the generation is the need for more reserves. So what some people have proposed is to use the fridges to solve at least one of the problems automatically. That's an example of what is called the dynamic demand, which is the dual of primary frequency support that is provided by generators. Generators that provide primary frequency support, they have a simple control loop that says that they add a delta to their production, which is positive or negative, and is proportional to the delta in frequency. That's the so-called droop control of generators. The idea that has been proposed currently in the UK in particular is to use the fridges for that. Why fridges? Why fridges? Yes, it's a bit elastic in the sense that it's a thermal load. So at least if you don't open a fridge, as long as it's not open, you can have some flexibility. If you make it a little bit cooler than it should be, 2 degrees instead of 4, then you can stop cooling it, and if you don't open it, the temperature will very, very slowly go up. So you have some flexibility in it. But there's another reason, is that the fridges are in fact a large load. Every fridge is not a lot, it's tens of watts, but it works 24 hours a day. And all houses have 1 or several fridges here. So it's like a permanent load that's running all the time, also at night, also in winter, also in summer. So it's a perfect system if you can modulate it. So there has been a proposal that so far did not make it through the regulator. In particular in the UK. Why is the UK more sensitive to this than the rest of Europe? There are fridges everywhere, not just in the UK. What is different in the UK or in Ireland than here, from the grid viewpoint? Yes?
Less inertia, less regional compensation.
Exactly, less inertia. The system is smaller. Great Britain counts only on Great Britain in terms of inertia. Ireland is even worse. The Irish grid, which is one grid for Northern and Ireland and the Republic, will be interesting after the Brexit what happens to it, by the way. It's an even smaller system. In smaller system, the inertia is much less, and then the cost of reserves is very large compared to the other costs here. So this is why they are more sensitive to this. And so there's a serious proposal that would say that fridge delays compressor when frequency drops and anticipates it when the frequency increases. Benefit of this is you don't need any communication system. I mean, a fridge is connected to the AC power supply. You put a circuit, a phase lock loop, for example, that will monitor the phase of the current. The frequency is the derivative of the phase, so you can simply compute locally the frequency. And then you have a system, for example, here, that says that you will try to control the on-off status such that when the frequency that is shown here on the y-axis, when the frequency is close to the nominal frequency, you do nothing. If the temperature does not allow it, but you allow that if the temperature is low, I guess it means low here, or for some time, I guess this is for some time, you will allow to do some control. The control means delaying or possibly anticipating the cooling of the fridge here. Of course, you want the fridge to still work as a fridge, so it still has a thermostat, and if for some reason the temperature inside the fridge is becoming too large, the compressor will go on. So your own fridge will not be jeopardized, but we count here on the law of large numbers. If there are millions of fridges that operate in this way, this will provide some support here. This has been analyzed for the UK, exactly, assuming only 10% of the consumption would react in this way. And essentially, the take-home message is that this amounts to the same thing as doubling the reserve. The reserve that's needed for primary frequency support here. So if the need for the reserve doubles because of more renewable, for example, the UK has a lot of wind energy that's being produced, which is also highly stochastic. If for whatever reason we need to have more reserves, then one of the possibilities is to use this. Similar studies have been done in the US with air conditioning, and over a very short time scale. So again, here we're talking of primary frequency support, for which those thermal loads are very good, because if you stop your air conditioning for half a day, perhaps the rebound effect will be very large. But if you switch it off for a few minutes, and of course if you randomize it appropriately, this works well. So similar studies have been done in the US for air conditioning, And some studies have been done only with the fans, not the compressors, but only the air conditioning fans of the large buildings. And they found that a very significant fraction, the numbers vary, but some sources mention 70% of primary or also secondary regulation power could be provided by those sources here. So we assume that in the future there might be a lot of interest in going in this direction here. Okay, we do a break now and resume in 13 minutes.